And for Bin, it's probably about what time? It's about 9 p.m. at night. So Bin's going to join us. He's the CTO and co-founder of Alluxio. Great. And he's going to give us a talk on big analytics in the cloud. So Bin, can you hear us?
Yes, I can hear you clearly.
Oh, wow. This is amazing. So I have a whole room of data geeks here in Singapore, and they're dying to hear what you have to say. So I hope you're ready.
Yes, I'm ready.
Okay,
Thank
great.
you.
Yeah, we'll take it away.
Yeah. Hi, everyone. Good morning, actually. I'm here to present how we build a data orchestration layer for big data analytics in the cloud. So as mentioned, I'm Ben from Alluxio, and I'm glad to be here and tell you our journey to build this data orchestration layer and what we can do for different use cases. So this is a little bit about me, and you have my email, my Twitter handle, and my GitHub account. A little bit of history into Alluxio. It was a research project called Taikiang in the early days. And you can think this is a sister project for Alluxio, for Apache Spark in UC Berkeley MPlab. And this was the research project, the PhD thesis for PhD student Haoyuan Li, who was the founder of this project. And later on in 2015, we open sourced this project and we established a company to commercialize Alluxio as a technology. But the company and the team is committed to move forward with the open source technology. And one of the founder is, and one of the investor is from the Andreessen Horowitz. We have different media coverage for the company and for the project. As I mentioned, this is the open source project, and we're so excited to see every day this open source community is growing. So far, we have more than 1,000 contributors in GitHub, and it's still fast growing. Our project has 4,000 more GitHub stars, and we have a community Slack channel. You are welcome to join us in the Slack channel to engage with the experts and also the community users. The software itself is under Apache 2 license. It's one of the most permissive license, just similar to a lot of other applications and software in the big data ecosystem. The software has been downloaded for more than hundreds of thousands times from our binary downloading and also from Docker downloading. I want to give you a little bit more history and also the motivation for why we're building this system. So if you go back to 10 years ago, that's how you are dealing with data ecosystem, big data ecosystem. On the storage side, you are pretty much using HDFS as the only storage solution for your big data analytics. And on the computation side, Hadoop MapReduce is perhaps the only choice at that time as a stable solution for you to be able to process and analyze a huge amount of data, like data at a scale. However, if you look at it today, the landscape has been dramatically different. On the computation side, we have been seeing more and more computation, especially open source computation frameworks, showing up, and they are getting more and more specialized in different subdomains in this ecosystem. For example, if you're dealing with streaming systems, Flink or like Spark streaming, might be your choices. And if you're dealing with key value stores, and this can be HBase or some other choices. And if you're dealing with interactive big data queries, and Presto or Spark SQL can be your friends. And even lately, we see a lot of choices in deep learning frameworks, including Caffe, TensorFlow, and many others. So the data ecosystem, the computation choices is getting more and more. And also the good news is we are also having a richer and richer choice in terms of how do you put the data. For example, in addition to the traditional HDFS, we also nowadays having a lot of users using Amazon S3 as the data lake to store a large amount of data. Similarly, for other cloud vendors, we see Microsoft Azure and Google Cloud Engine. Yeah, so you still see more and more different choices from either cloud vendors or from hardware vendors to provide solutions to store big data. And given this change in the past 15 or 10 years, we also see a very interesting journey associated with a lot of different companies in terms of building their big data ecosystem, big data infrastructure inside. A lot of companies or organizations, they started with a co-located compute for HDFS and a compute and HDFS. So basically you deploy a bunch of boxes. In each box, you're running MapReduce daemons and HDFS daemons. So in this way, you are deeply optimized for data locality. Instead of moving data to computation, this is basically followed by the Google file system paper, a MapReduce paper that following the philosophy moving computation to data. So this is great, co-located compute and storage. However, this typically results in compute-bound storage, compute-bound cluster, and it's very hard to scale computation and I/O independently. In this case, because these two dimensions are deeply coupled, it's very hard for you to say, I just want to buy more CPU resource, rather than just also spending time in investing on disks. For a lot of use cases, we see users are exploring the architecture to have disaggregated compute and storage. Essentially, the idea is have a different set of machines running. One pool is running computation, the other pool of machines is running like storage, like HDFS. So we have this disaggregated compute and storage, and this will give you the flexibility to independently scale two dimensions. However, a lot of users are still complaining, if I want to store all my bytes on HDFS, this can be expensive. We see a typical journey nowadays in recent years. People are talking about how to share data across data centers, but without changing the applications. And also another very popular choice for a lot of enterprises is to seek the opportunity to burst their workloads. For example, burst their HDFS data into the cloud, public or private cloud. And when you burst this data into the cloud, you don't have to always use the computation resource from the cloud, but you just always pay and just pay for the resource you need. And in this case, you get a much better efficiency in the resource efficiency. And also, another trend we see is to migrating their HDFS, conventional HDFS data as a lake to a cheaper, more scalable, and easier to maintain services like Object Store. So this can enable and accelerate big data on Object Store, but migrating data from HDFS. So these are the data stack journey we see in the past few years. And this is what we're proposing. Our motivation is to build another layer into this data stack. So instead of having better computation or build a better storage, we realize that either computation and storage, they are evolving constantly due to new hardware, due to new workloads. So what we're doing here is to build another layer between the computation and storage. And you can think this as a data orchestration layer providing a data abstraction and also data policies. In our northbound, we call it like our interface talking to application because it's northbound. We provide different popular APIs representing the same data abstraction to Presto, to Spark, to MapReduce. And to our southbound, there are drivers talking to this physical and maybe remote or disparate physical storage engines like S3 or Azure or HDFS. So in this case, we can provide the data abstraction. In this case, applications don't need to worry about, oh, how do I connect to each individual physical data source, but just talk to this abstraction, that's good enough. And within this layer, we can install different data policies, including data caching. For the hot data, we can cache data in this layer, including setting TTLs, including migrating data from one physical store to the other, including some time-based policies like synchronously or asynchronously propagated data from one layer to another. So there's a whole lot of different things you can do with this new data orchestration for the cloud. So in this slide, I want to show you a flavor how users are interacting with this layer. As you can see, for applications like Spark or Presto, which are leveraging HDFS interface as their way to access data, it's basically the same semantics. You just change from HDFS, / into Alluxio, //. Because we also provide a POSIX compatible interface, and you can mount Alluxio as a service into your local laptop or local desktop. And then you can use your familiar Linux commands like cat or ls or du to check and see and read and write data from this Alluxio service, just as you're interacting with your local files in your local folders. And in the end, we also provide a Java API, which is very similar to Java file system. And this is the file system API you can leverage most or the complete set of functionalities from Alluxio. So yeah, so we provide the same set of data abstraction, but through different APIs, up to the choice from the users. I want to go through a few use cases we think most relevant to the audience here. The first case is as a distributed caching layer for cloud storage, like GCS or S3. We know that for S3, the performance can be variable, and also if we want to ensure consistent query latency as a SLA, sometimes it's hard to achieve because S3 just like it's remote to our application, and also it's just like a black box. And what's more, a lot of metadata operations to S3. S3 is not really a file system, so a lot of metadata operations like listing buckets or rename a object can be expensive because S3 implementation is different from the file system. And the egress costs may adding up and also making the solution more expensive if you just migrate data constantly to the cloud. Finally, the eventual consistency is very well known that it's a trouble for a lot of applications, which is not designed to dealing with this kind of override the eventual consistency when overriding an object into S3. So in this case, we see a lot of users are applying Alluxio as a co-located distributed storage caching layer for applications like EMR Spark or EMR Presto or their own applications. So you can install Alluxio in this way to bring up the data locality, which is missing in this picture. So thinking this way, if Spark is directly talking to S3 or GCS, then you don't have data locality anymore, right? You always drag data from the remote data service. And in this case, if you with Alluxio, in this case, if you are accessing data with some data locality, then this will save you the traffic reading repeatedly from S3, but also provide you a more consistent and low latency data retrieval. The next use case we see in a lot of cases for a lot of users is to use Alluxio as a data federation layer in a hybrid cloud. So thinking this way, if you have a data in HDFS, but you want to leverage the objects, the resource, public vendors, like you're running Presto there, but you don't want to really retrieve data repeatedly from HDFS, then you can just install Alluxio there as one layer to hide this. Deploy the same architecture in the opposite way. You can move your data to cloud storage and run computation in your on-demand, in your own data warehouse, and using Alluxio as the layer to access data. And you can have data in both places, in both S3 and also in your own data warehouse, and using Alluxio as the federation layer to unify, because we're providing a data abstraction, and it doesn't matter where data is really physically and persistently stored. And using this data abstraction layer, your applications, your logic to deploy and maintain applications can be very simple. So this is basically our vision in the long run. If you can have a data orchestration layer, and you may have different choices to run your applications in your own data centers, you may have even multiple different data centers, and you can have part of applications in your your resource rendered from the public cloud vendors. And then by having this data orchestration layer, it will just make everything very simple. Everyone is seeing the same data abstraction, and the data migration, the data persistency, and also data propagation will be handled by this orchestration layer without applications to worry about how do I really enforce these different policies your company or your environment really wants to achieve. Yeah, so the key innovations in order to achieve this orchestration layer include a lot of engineering work to improve the data locality by having something like a multi-layer caching, and the data accessibility by providing different popular APIs and API translation on the server side, as well as data elasticity with a unified namespace. I will go through the three bullets in more details. This is how we improve data locality. So essentially, we build a distributed storage engine, come up with Alluxio. And within this engine, you can allocate different tiers. One tier, for example, one tier is allocated with RAM, one tier is allocated with SSD, and one tier is allocated with hard disk, or some combination like this. And because we are not targeting as a storage, this is really, we're just trying to optimize the performance, optimize the data layout, data storage for computation, the performance of computation. So we will tell, okay, some part of data is very hot. Let's just cache the data into this layer. And some other part of data is not that hot, it's warm. Okay, let's maybe put it into the SSD tier. And some code data can be put into hard disk tier. Some other data, because they are not used according to the prediction for data access pattern, we can maybe just evict them out because the entirety of the data is still stored in the persistent storage. So it doesn't matter if we evict them out. Next time, if the application needs them, we can just always transparently load them back. So this is how we achieve data locality with the multi-tiering caching to improve the local performance from reading remote data. As I mentioned earlier, we provide different interfaces, and for different applications, they may have their own favorite interface. For Spark, Presto, or Hadoop MapReduce, typically they want to use a HDFS interface. So that's one way to access the data abstraction. But for more trendy TensorFlow or Caffe, this type of deep learning frameworks, they are more used to access data and assume data is on a local disk. So they can use our POSIX interface. And to our southbound, because we have a set of different drivers talking to the physical stores, then we can always choose. This is basically under the hood and it's transparent to the users or applications. So we can always choose dynamically which drivers to use to access the data, including the S3 driver, HDFS driver. The interesting part is we can even use a different version of HDFS driver than the HDFS interface we're exposing. For example, we can talk to HDFS 1, but we are exposing HDFS 3 as an interface to applications. Or we can have multiple HDFS drivers, one in version 1, one in version 2, one in version 3, and we combine them into one single namespace and exposing a single HDFS 3 interface to the applications. So this is the power, this demonstrates the power of having this indirection and having this abstraction layer. So the last part is about the data elasticity, how we achieve unified namespace. So essentially on your laptop, you can easily mount different disks into your local file system because they all implement for example, the Linux VFS API. So in that case, we can just mount it as a different implementation for this VFS device. And it's a similar case here, but instead of having a single node file system, we extend this idea to distributed and remote file systems or storage systems. So you can mount a S3 bucket into one of the directory in the Alluxio logical file system. And you can also mount, for example, the HDFS to be the root for the logical file system of Alluxio. Here we see more cases by adding Alluxio as a POSIX API, by mounting the POSIX API and mounting Alluxio as a local folder. The service show up as a local folder. In fact, different directories are backed by different storages. But from user's perspective, this is hidden, this is transparent. So we have a lot of companies using Alluxio, and I will go through a few cases that might be relevant to the topic here. So one use case is from a digital marketing company in Austin. Their use case is to accelerate their data access pattern from Hive to AWS S3. So they have a lot of data stored in AWS S3, but they also only want to cache certain partitions. So these certain partitions, they are frequently accessed by a lot of different jobs. So in this way, their Hive jobs do not need to repeatedly go to S3 to read the data. And the way they achieve this is to deploy Alluxio co-located with Hive, and for certain partitions to cap, for example, the latest 30 days. And for the latest 30 days of the data will be stored in Alluxio, but the entirety of the data is still in S3 as a data lake. So in this way, they claim they see a 10x performance gain by having the memory first data approach. And here's the link to access their blog. So we have another use case from China Unicom, and they are using Alluxio as a way to speed up their Spark performance. And originally they have different data source for Spark to process. They have to run ETL jobs to drag data from one data source to their Spark cluster. So by having data orchestration like Alluxio, besides running together with a Spark and hiding the work to loading data from the external storage into this storage running Spark, then they can save the cost running ETL, and also because the memory first approach, you get a much more performance gain. Yeah, so the rest of part of the talk, I will go through very quickly about the architecture, how data flow in Alluxio. So similar to most of the distributed file systems, we have the master nodes managing the metadata and the worker nodes managing the real data, serving the data to the cloud. And unique point in this picture is we do have a concept called understore, which is the persistent layer for the data. So Alluxio workers you can think this provides a distributed caching layer for the data, but the persistency for the data is provided in the object store or HDFS you mounted into Alluxio. And inside Alluxio, each logic file is divided into logic blocks. And one logic block can be in one worker or multiple workers. And the same blocks can be replicated multiple times. Also, different blocks can be distributed differently across different workers to achieve load balancing and also to have higher bandwidth to access. And in the end, we also provide a way to for users to set their own block size according to their use cases. And what we see is if you're running the traditional MapReduce jobs, which reading sequentially for a whole lot of data in one file, and the default big block size can improve the performance. If you're running the SQL workloads, running to read the files from like a Parquet files, and then smaller block size can result better performance. And this is basically the architecture for the master. You have the RPC service to cover the file system metadata, block metadata, and also worker metadata. And because we provide efficient, we're another layer. We also serve metadata on top of S3. We can avoid the expensive bucket listing in S3, and this becomes a very key and important optimization for Spark SQL or Presto workloads. And also the rename becomes very efficient because in our land, this is still a very easy inode change versus in S3, rename becomes a copy and a delete. And also we batch understore operations to S3 to have higher performance. And here are the different sources how we can achieve better and more efficient metadata operations on S3. And on the data side, we provide a data service, and this is the different like RPC service and also data transfer service on the worker side. And we apply different innovations like to avoid JVM GC, we store the blocks off heap, like for example in the RAM disk, and we have tiered storage to manage the data. And in the latest version, we also use the gRPC-based streaming RPC service stub to improve the data throughput. And we provide a way to asynchronously archive data to S3 from, you can write data Alluxio first and then asynchronously persist data to S3. So yes, here, because we're adding a new layer, we are having different modes to write and read data. For example, we can read data. If the data is already in Alluxio, then we just read this directly and co-located, and this will provide you best performance. If this is not cache hit, but rather than cache miss, then the client will talk to the master, and the master will instruct a worker to fetch data for this client. And meanwhile, you can just also cache the data into this local worker. So next time when the same client is if any client is requesting the same block data, and we will be able to serve this from Alluxio space. Similarly, on write path, because we have the new layer, you can either choose to write to this Alluxio layer only, which is shown here, or you can decide to write data persistent to understore asynchronously. So after this operation completes, you know the data will be cached into Alluxio space, but also persisted into the understore. And in a 2.0 release, we also provide a new approach. You can write the data to Alluxio space first, and then asynchronously to the understore. And we have a lot more interesting architectural improvements in a 2.0, which is released last month. So this concludes my talk, and I'm willing to take a few more questions.
Thanks, Ben. Any questions for Ben? All right. Well, Ben, thank you for joining us remotely. We appreciate your efforts.
Thank you. Thank you.
Have a great evening.
Have a good day. Bye-bye.
Bye-bye.